Today we're going to be talking about antiderivatives and indefinite integration. So here in this example, we want to look at all of the possible functions with this given derivative. So what functions could have that derivative? Well, I could have the function 1/3 x cubed plus 7. I could have the function 1/3 x cubed minus 9. I could have the function 1/3 x to the third plus 487. So if you notice the pattern here, I could have any function plus some constant. So a function f is called the antiderivative. That's a key term. So the antiderivative of a function over a given interval if the derivative of that function equals my function for all x on the interval. So the process of finding antiderivatives is called antidifferentiation or integration. This is honestly the term that I use. And when integrating, when integrating f of x, it produces the antiderivative big F of x plus c. And we denote that by looking at this formula here. So looking at the earlier example we had, this would be equal to 1/3 x to the third plus c. So our rules for integration, or when you're taking the antiderivative, basically when we're undoing the power rule, okay? You add 1 to the exponent and then 1 over your new exponent. Remember, this function is the derivative of this function. So all I have to do is take the derivative of this function to get that inside function. So here, looking at this, what I always do is I always do x, I get my new exponent, 1 over my new exponent plus c. Now, if we were to take the derivative of this, we would take the derivative of that top function and bring down the 5. 5 times 1/5 is 1. Reduce your exponent by 1. Derivative of a constant is 0. So notice how this and that are the same thing. What I would do here on this example is I would rewrite this as x to the negative 1/5 dx. So, and then I add 1 to my exponent, 1 over your new exponent, and don't forget your constant. That's called the constant of integration. Don't forget your plus c. The next example, what I would do is I would write this as x to the 4/3 dx. Having this dx is important. We're going to talk a little bit more about what that dx means in future lessons. For now, I'm going to just ask you to accept that it's there. Okay, we'll talk about what that means in a few lessons. I apologize. Anyway, add 1 to your exponent. So I add 1 to my exponent to get my new exponent times by the reciprocal of that exponent. And don't forget your plus c, your constant of integration. Okay, so some properties now of integrals. Basically, there's some similar properties. I can take a constant out in front, and then I can take the antiderivative or the integral of each term. So looking at this, I can take the antiderivative of each one of these terms individually. So the antiderivative of x to the third is 1/4 x to the fourth minus 2x squared plus 2x plus your constant c. Now, you're going to get really used to this. Even right now, I'm so used to doing derivatives, so I'm struggling a little bit with actually taking the integral. You'll get really used to it, okay? It's just going to take some time. Trig integrals, okay? Keep in mind that this piece here, these, if you take the derivative of those, you get all of these functions, okay? So it's kind of like Jeopardy. Like what function's derivative is cosine is sometimes what I think of it when I'm doing a more challenging integral, like trigonometric integrals, okay? So I'd make sure you pause this video and make sure you write all those down in your notes. It's something you're going to need to memorize. Okay, now doing some trigonometric integrals. And really some more manipulations with integrals. There's no rule of integration where we can integrate the top and integrate the bottom. I can't distribute the integral symbol to the top and the bottom. So both of these I have to manipulate in some way. So cosine, well, 1 over sine cosine of x over sine of x. I now have cosecant x times by cotangent x dx. So what function's derivative is cosecant cotangent? Negative cosecant x. And again, don't forget your constant of integration. This next one, we need to manipulate. You can't just take the integral of the top and integral the bottom. So what you need to do is, since the denominator is only one term, I can separate this out into t to the fourth over t, I apologize. I can separate this out into t squared over t to the fourth minus 2t to the fourth over t to the fourth dt. And then I'm going to write this with a negative exponent. I'm going to simplify that to just 2. So now what I can do is I can now take the antiderivative of this. So adding 1 to your exponent, ooh, this is a fun one, negative 1 over your new exponent minus 2t, don't forget your plus c. This is actually in a later section in our book, but I want to introduce it, okay? Remember, the derivative of e to the x is e to the x. So this one's actually my favorite integral, okay? This one, I want you to know, doesn't come up a whole lot, but I want you to know this one. And then the antiderivative of 1 over x, okay, so what function's derivative is 1 over x? Well, that's ln of x. So 3 to the x dx. The antiderivative of that is 3 to the x over ln of 3 plus c. Again, you could take the derivative of this. Derivative of 3 to the x is 3 to the x times by ln 3. You have that ln of 3, because that's a constant in the bottom. Those cancel, so that's how I get that value up there. For e to the x. Remember, you can pull a constant out front. And then the antiderivative of e to the x is e to the x plus c. I really like that one. And then lastly here we have negative 3. I can pull the negative 3 out front. 1 over the antiderivative of 1 over x. What function's derivative is 1 over x? Well, that's ln of x with some absolute value signs in there, plus c. And I want you guys to think about why I might be putting those absolute value signs in. Let's talk about that in class, okay? Okay, now we're going to kind of get that c to go away. Okay, so what function's derivative passes through the point c? Okay, so let's look at this. What function's derivative is cosine of x? Well, what function's derivative is cosine of x? So I take the antiderivative of cosine of x. Okay, now I need to think what function's derivative is cosine. Well, that's sine of x plus c, and that's going to equal f of x. Now I have this xy point that I know is on my graph. So I know -2 equals the sine of 0 plus c. Sine of 0 is 0. So now we have our function. We've gotten rid of that c. Okay, I'm going to skip down to another example. I'm going to skip example 5 because I'm going to go right to number 6 because 5 and 6 are very similar, and to make it not too long of a video for you all. Okay, so this one. So we know the derivative of position is velocity, and we know the derivative of velocity is acceleration. I shouldn't have that prime in there. Let me erase that. Now if I integrate, okay, if I integrate velocity, if I integrate acceleration, that's going to get me my velocity function. If I integrate position, if I integrate my velocity function, that's going to get me position. Okay, so here I have my acceleration function. So if I take the antiderivative of this with respect to t, because that's my variable, I have 2t squared minus 10t plus c. Remember, I took the antiderivative of acceleration, so the antiderivative of acceleration is my velocity function. This is called an initial condition. I give us an initial condition. I tell us the velocity at t equals 0 is 3, so that goes to 0, that goes to 0. That gets me my c. Now, I take the antiderivative of velocity. The antiderivative of velocity is position. I'm going to have 2/3 t cubed minus 5t squared minus 3t plus c. Again, I have this initial condition that gets me c. So now I have my position function is 2/3 t cubed minus 5t squared minus 3t plus 12. So that is your introduction to antiderivatives. I hope you enjoyed that.